Okay, we are now into the very last section of the class, where for the first time all semester, we begin to deal with the fact that things happen in time. We start talking about rates, how fast things happen, and not just where they end up after they've reached equilibrium. So it's hard to overemphasize how important chemical kinetics is. The thermodynamics and statistical mechanics that we've been talking about so far sets the structure for why things move and where they'll end up if you wait long enough. But there are many, many processes, both in chemical research, but also 10 times more in the wider world, where how fast things happen determines not just, well, how fast things happen, but also how things end up. If you have some process, for example, that can go one of two ways, but one way is 10 times faster than the other, then effectively the slower way, even though it's a possibility, gets swamped out by the much higher rate at which the fast thing happens. And so the rate at which things happen can also determine the outcome of the overall process, even though it's not an equilibrium situation at the end. So chemical kinetics is a branch of what's called non-equilibrium statistical mechanics, which is a large and important field. What we've been studying so far is equilibrium statistical mechanics. There's also non-equilibrium statistical mechanics. And non-equilibrium statistical mechanics deals with everything that involves time or rate or speed. It's a huge and subtle field with a lot of really cool results and cool ideas. It's the area probably where the center of my own research and thinking has been for quite a few years now. And I would love to talk about it, but it is also complicated and even more mathematically complicated than the equilibrium stat mech section we just went through. And we don't have very much time in the semester, and in any case, it's kind of a topic that's usually relegated to more advanced classes than this one. So for all those reasons, we won't talk about it, but it's good that you know that it exists. There is more than chemical kinetics. There's a little preview of it in the book, in the two chapters that we're skipping. We're skipping chapters 16 and chapter 17, which are the kinetic theory of gases and then transport phenomena. Both of those are examples of at least the very, very lowest level and beginnings of non-equilibrium stat mech. So if you want to get a little bit of a flavor of it, especially the transport phenomenon section in chapter 17, then you can look at those chapters, but we won't cover them in this class. Okay. So we're going to focus on traditional chemical kinetics, and to do that, we are going to go over the basics. I'm going to assume that everybody has seen these basics at least once before. I know from the fact that I teach freshman chemistry sometimes that all these things, pretty much all these things, are taught at least at some level, even in freshman chemistry. So probably all of you have seen a little bit of it at least before, and that means we won't dwell on it as long as we would if this were the first time everybody had seen it. In order to go through this section, it is useful to have a couple of standard chemical reactions in mind. When we're talking about general cases, I'll use this standard sort of abstract chemical reaction, AA plus BB goes to CC plus DD. And when we want a really concrete example, for the most part, I'll use this water-forming reaction, 2H2 plus O2 goes to H2O. All right, the very first thing we need to do in order to talk about kinetics is define what we even mean by the rate of reaction. And there is a sort of standard definition which we'll talk about in a minute, but that standard definition is rarely used in the chemical literature. Much more often there's a sort of informal definition that any rate of change of any concentration-like quantity can serve as a rate of reaction. So if I've got this generic chemical reaction and I take the time derivative to calculate the rate of change in the concentration of A or B or C or D, any of those can be called a rate of reaction. Under common circumstances, those four rates are in fact related to each other, and they're not all independent of each other. If you know one, you more or less know all of them, and in that sense they can all be used as a rate of reaction. We'll talk about that condition in a bit, but before we do that, let me also mention that while concentration, molar concentration for the most part, is the most widely used variable for following the rate of reaction, other variables are sometimes used. Pressure and other types of concentrations, and even instrumental signals like signals out of a spectrometer and things like that are used for rate of reaction when they're used experimentally to follow how fast a reaction is taking place. So for example, for this water-forming reaction again, taking the time derivative of the concentration at which water is appearing, water in the gaseous form is appearing in the reaction is one way to define and talk about the rate of reaction. But if somebody wanted to follow the rate at which the pressure of water vapor was changing, that would also serve, and in many places in the literature, that's the kind of thing you'll see. All right. It turns out that an important distinction in kinetics is whether or not the overall reaction that we're talking about, so this abstract one, let's say, has any intermediates or not. An intermediate is a chemical species that doesn't appear in the overall reaction. So here, A, B, C, and D are all the species, all the majority species. Those are the things that actually appear in the overall reaction. But there may be other species that are actually generated in the course of this chemical reaction but aren't listed in the overall reaction because they're consumed as fast as they're created. So there isn't any overall creation of those species. Those things are called intermediates. So if a reaction has intermediates, then we call it an overall reaction, and its behavior is a little different than if it doesn't have intermediates. If it has no intermediates at all, if everything that's actually created in the reaction is listed in the reaction as written, then it's called an elementary reaction. And we'll talk a lot about elementary reactions. Kinetics is all about elementary reactions. They're the important thing. These overall reactions, like this one maybe, are composed of elementary reactions. There's more than one reaction going on, even though you write just one reaction to describe the overall process. All right. If the reaction has no intermediates, so if it's elementary, or if the intermediate concentrations are there, but they're not changing with time, so steady state intermediate concentrations, then the following relationships hold. These relationships hold. Very often in textbooks, probably in other places when you've seen, when you've learned about kinetics before, these relationships are presented as unquestionable truths, but in fact they don't always hold. They only hold if there are no intermediates present, or if the intermediates are at steady state. That covers a good deal of the time. Very often the reactions we're talking about are elementary, and then there are no intermediates. And even when it's not an elementary reaction, very often the steady state, the intermediate concentrations are at steady state, and then these relationships will hold anyway. But there are circumstances where they don't hold. So these are useful relationships, and we'll talk about them and use them a lot, but remember that there are circumstances where they don't hold. All right, what are those relationships saying? They're saying that if I have a chemical reaction with, let's say, 4 different species, like in this abstract reaction, that the rate at which one of the species changes is related to the rate at which all the other species are changing. Why is that? Well, because according to this overall reaction, if I lose A molecules of big A, then I have to also lose B molecules of big B, and I have to also gain C molecules of big C and D molecules of big D, and that means that the rate at which I, say, lose A molecules is going to be related to the rate at which I lose B's and the rate at which I gain C's and D's. It's the stoichiometry that's controlling that relationship. And so, quantifying or formalizing that a little bit, we have that if I divide each time derivative, each rate of change for a concentration by its own stoichiometric coefficient, and if I put a minus sign in front of the definition or the term for a reactant, so minus signs for reactants here, and a plus sign, or no sign really, for the products, then all of those quantities are the same thing. If I take the rate at which A's are disappearing and divide by the stoichiometric coefficient, do the same thing for B, do the same thing for D, do the same thing for D, and then keep track of the signs so I know which ones are disappearing and which ones are appearing, right? The minus signs make this a positive quantity if A is going away, right? If A is disappearing, then this time derivative is negative, and the minus sign makes it positive again, which agrees with what's going on over here, right? Assuming the products are building up. So the minus sign is to make the signs match between all those terms, all those quantities. All right, so we have this relationship then most of the time, not necessarily all the time, but most of the time. And so to take an example, let's take our concrete water-forming reaction. That means that minus 1/2, the rate at which H2 is disappearing, is equal to minus just the rate at which O2 is disappearing, and that's equal to 1/2 the rate at which the water is appearing. Okay, so we have a definition for our rate of reaction. Very often this thing is called R, capital R. It's called the rate of reaction. But as I said earlier, this term R, or this formal definition of R, isn't universally used. People sometimes use other effective definitions for R. In this class, we will use this definition of R when it's convenient to. We'll ignore it when it's convenient to ignore it. All right. I mentioned a minute just now about overall reactions versus elementary reactions. And I said something about what the difference is between overall and elementary reactions, but let's talk a lot more about that because the concept and properties and uses of elementary reactions is really central to all of kinetics. Let's suppose we have our water-forming reaction here. So this is 2H2 plus O2 goes to 2H2O again. And here I've drawn out the actual molecules to emphasize the fact that a lot is going on in this overall reaction. This is not an elementary reaction. This is an overall reaction, which means that there are intermediates present when this reaction takes place. We'll see down here there's a mechanism that's composed of a bunch of smaller, simpler reactions. And that's the process by which this overall reaction actually takes place. And knowing what that process is necessary to understand the kinetics of this overall reaction. And to emphasize that even more, I drew out these molecules because it shows what's really going on. I have an H bond here, an HH bond. I have an HH bond here. I have an OO double bond here. And on this side, I've got 4 OH bonds in water molecules. Obviously, this didn't all happen in one step. It wasn't that all these molecules got themselves into a little ball and suddenly decided to swap all their bonds around. No, what happened was something like what's shown in this mechanism down below. Now, this is not the official mechanism. The official mechanism for this reaction is actually a good deal more complicated. But I use this mechanism because it's complicated enough to show all the principles involved, but not so complicated that it makes a mess of things. So don't take this to be the official mechanism. In fact, let me write, this is the unofficial mechanism for this reaction. And this reaction's been studied a lot, and there are elaborate and well-founded experimentally mechanisms for this reaction, but this is not that. This is just an example really for this class. But let's look what it says anyway. It says, first of all, you've got an H2 molecule here, and spontaneously on its own, it just breaks into 2 H atoms. Does that happen very often? No, it happens extremely rarely. The HH bond is quite strong, and the odds that after a collision or something, the H2 molecule gains enough energy to actually break its chemical bond is really rare, but it's not zero. It happens. Once it's broken, I mean, there's Avogadro's number of molecules running around all the time, and there's a zillion collisions per second happening all the time, so even very rare things happen. Once it happens, you've got, well, sometimes these things are written with a dot on them to indicate that this is a radical, right? It's a loose atom with an unpaired electron. It's really reactive. The very next thing that's going to happen is that H atom, either of these H atoms, is going to collide with something, anything, and then it's going to react as soon as it collides because it's a really reactive species. So in this case, one of the things it can collide with is another oxygen atom. Those are around. And one of the things it can do, if it collides like that, is it can basically steal an oxygen atom from the O2 molecule and create an OH radical. So oftentimes that's also written with a dot to indicate that there's an unpaired electron in there, right? Because we're missing a bond. There's a dangling bond, as it's so sometimes called. There's an H and an O, but it wants another H over here, right, to make a full water molecule, and that's missing. So it's still got a broken bond in effect. And still very reactive. This is another radical, another reactive species. And then another very reactive species, another loose O atom, which for the same reasons as the H atoms is also very reactive. So we've started with one reactive species and ended up with two in this reaction. Now both of those can run around and collide with other things. And so in this case, an O atom can collide with another H2 and steal one of the hydrogens from that H2 and create another OH and leave behind another loose H atom. So now you've got still more radical things happening, or high energy radicals created. And then one of these OHs can collide with another H2, steal an H atom from that H2 and create a full water molecule finally, and leave behind another loose H atom, which can then run around and participate in the rest of this mechanism and go on to eventually create more water molecules. So that's an example of a mechanism. There's four, each of these are elementary reactions. And there's four of them, and all four of them combine in order to give rise to the overall process that's indicated by the overall reaction. The overall reaction isn't telling you about what's going on microscopically. It's just telling you about the stoichiometry. It's just telling you that there's two H's and one O in order to create two H2Os. But it's not telling you about all this stuff that's going on with the actual atoms and molecules. So the overall reaction is useful, but you still need a mechanism in order to do kinetics. All right, so for an elementary reaction, I said above, for any of these four here, there are no intermediates, and that means this set of relationships up here between all the chemical rates holds for each of these reactions independently, individually. But, and we'll talk more about what makes something elementary. Well, I mean, the thing that makes a reaction elementary is the fact that it doesn't have any intermediates. That's the definition. But we'll talk more about what physically makes it elementary, too. Basically, it's a very simple process that doesn't need any intermediates in order to take place. For example, in this case, it's just an H bond breaking. That doesn't require any intermediates. That happens all at once and all in one step. And that's the kind of thing that elementary reactions generally are. But notice that in this reaction, in this one, for example, we're creating H atoms. In this reaction, we're creating OH radicals and O atoms. In this reaction, OH radicals and more H atoms. And here we've got OH radicals combining in order to finally form water and more H atoms. We've got three chemical species here, H and O and OH, all of which don't appear in the overall reaction. And that's the signature that they are intermediate species. And the fact that those intermediate species are there tells you that this reaction is not an elementary reaction. It involves elementary intermediates. But there aren't any intermediates that you need to take into account what's going on with any of these. I said a minute ago that this is just a simple bond-breaking reaction, no intermediates there. This is just a simple collision between two species, no intermediates there. Another collision here, another collision here. So unimolecular processes, meaning in this case a single molecule is involved, those are usually elementary. And bimolecular processes, things that involve a single collision by a single pair of molecules, those are also usually elementary. And in fact, when something involves only a single molecule like this, then it's said to have a molecularity of 1. And when something involves two molecules like this, or two species like this, then it's said to have a molecularity of 2. And in principle, you could have elementary reactions with molecularities of 3 or 4 or higher. In practice, as I'll say again down later, things with molecularity of 1 or 2, that is either unimolecular reactions like this, bond breakings, rearrangements, those kinds of things, or else collisions, those are really the main, by far the most common types of elementary reactions. And in fact, it's exceedingly rare that you ever get a molecularity more than 2, like 3 or something, outside of textbooks anyway. All right, so we now have that for elementary reactions, these relationships hold, generally not for other things. And let me say something about that. Why do these relationships amongst the reaction rates not hold when you have these intermediate species involved? Well, if you've got intermediates, then it's no longer true that in order to lose A molecules, so here's our reaction, right? This set of relationships is based on the idea that when you lose A molecules of A, you also have to lose B molecules of B, and so on. But if there are intermediates around, that isn't true anymore. You can lose a bunch of A's and they go into creating a whole bunch of intermediates and don't even show up in this reaction at all. So as long as you've got significant amounts of intermediate being formed, and as long as those concentrations are changing in time, either building up or decaying away, then these relationships won't hold. But most of the time that isn't true. Most of the time the intermediates are present only in very small concentrations, and or they're not present at all in an elementary reaction, or they're not changing with time because the reaction's in a steady state case. In all those cases, these sets of relationships hold at least as a very good approximation. All right. So that's the very most basic stuff for defining chemical reactions. The next step, or the next piece of the overall body of ideas, is to define what we call rate laws. A rate law is a connection between the rate of reaction and the concentrations of the species involved. So it's something like this. This is the most common form for a rate law, a power law rate law. It's not the only kind that can happen. It's the one that you'll always see in low-level textbooks, freshman chemistry textbooks, even in our textbook, though our textbook does, to its credit, point out that there are other kinds of rate laws. But it is by far the most common kind. And so what I mean by power law is that a rate law like this has the following elements. It's got something called a rate constant, and that rate constant is the subject of an intense amount of interest. And the reason it's of interest is that because it controls the rate of chemical reaction. But it's also the only place in all of what we're going to talk about in the first part of this whole section where there's some information about the nature of the chemical reaction, right? Everything else is just what's the concentration of stuff in solution. It doesn't tell you about what's in solution. It doesn't tell you about whether it's water or hydrogen or ammonia or any other molecule. All that information is buried inside this rate constant. And furthermore, these rate constants are extremely complicated to calculate from first principles. So they're hiding an enormous amount of complication. And that's a good thing when you're just beginning, right? Because you don't want all that complication at the beginning. Eventually, you want to understand all that stuff. You want to understand what goes into that rate constant. But first, you want to see what the rate constant just does, what effects it has. And that's the stage we're at right now. Then there's a concentration for one of the chemical species and raised to a power. And that's called the order for A. And then another chemical species, and it also has an order for B. And in principle, you can have more terms here. I have a little ... there to indicate that there could be a C to the gamma and a D to the delta. As many powers as it takes out here to describe what's going on in your chemical reaction. Usually, 2 is sort of the limit of things. I can't remember ever seeing, in fact, a rate law that has 3 or more terms, but in principle there could be. These powers are usually integers, usually positive integers. So the orders are usually positive integers, but they don't have to be. In principle, those powers can be anything, and sometimes they are not integers, and occasionally they're not even positive. So you can have orders for a rate law that are crazy. You can have, an alpha, say, of 1.77 or something like that, and that's perfectly fine. It can even be minus 0.6 or something like that. There's nothing that prevents that from happening. We'll talk later about where these rate laws come from, and you'll see why they're usually positive integers, but they don't have to be. All right. There is a third type of order that's important. So I said that this guy, the power on A, is the order for A. Power on B is the order for B. There's also an overall order, and that's just the sum of the two. Or if there were more terms, the sum of them all is the overall order. All right. That's just a bit of terminology. So here's an example down here. In this case, for this rate law, there's the rate constant. This is first order in A, because there's a 1 here, right? And there's nothing else, so it's 0 order in everything else, right? A B to the 0 power is the same thing as not having a B term there at all. And so everything else is 0 order, and that means the overall order is also 1. In this case, this rate law is second order in A, 0 order in everything else, and second order overall. And this rate law is first order in A, first order in B, 0 order in anything else that may be around, and second order overall. First order in A and first order in B is 1 plus 1, second order overall. Okay, now, in an overall rate law like this, the rate constant that appears has to have units. The rate itself is always got units of constant. Well, let's narrow the focus to just cases where we're talking about concentrations, molar concentrations. In that case, the rate is always in units of molar per second, right? Rate of change of concentration, so molar per second. And over here on the rate on the power law side, you've got units of molar to the alpha here. You've got units of molar to the beta here. And so this overall term combined has units of molar to the alpha plus beta power. Well, the units have to match on both sides of the equation. And that means that this rate constant has to have units which depend on the overall order of the rate law. So notice that this alpha plus beta is the overall order of the rate law. That means that in order to make the units match on both sides, this rate constant has to have units of molar to the minus alpha plus beta minus the overall order plus 1 to give this molar units over here, and then seconds to the minus 1. The seconds to the minus 1 never changes, but the power on the molarity part of the units on K does change depending on the overall order. So for first order, using this rule here, the units on K will be seconds to the minus 1, or 1 over seconds. For second order, it'll be molar to the minus 1, seconds to the minus 1. I imagine people have seen those kinds of units on rate constants lots of times already. If it's a half order, for example, the overall order is a half order. That would be something like R is equal to Ka to the 1/2 power. That kind of thing happens. It isn't even that rare, actually. A half power is not real common, but not at all unusual. Then the overall order is a half. Alpha plus beta in this case is a half. Alpha plus beta minus plus 1 is minus a half, plus 1, which is plus a half. And so the units for the rate constant, this guy, in this case, are molar to the 1/2, seconds to the minus 1. You can have weird units on rate constants if the overall order is a weird power, like 2/3 or 1/3 or pi or something like that. All right. Now, I've been talking in general up to now. All this, everything I've said so far applies to every kind of reaction, whether it's overall or elementary. But for elementary reactions, we can say a good deal more. And so everything I'm going to say for the next little bit has to do only with elementary reactions. And doesn't work for overall reactions. So you've got to be careful when you're using these results to make sure that it's an elementary reaction that you're talking about. First of all, I said up above that elementary reactions have molecularity. There's molecularity 1, or first order. That's a single molecule going to some kind of product, and it doesn't matter what those products are. Sometimes, like in the case up above, where it was H2 going to H plus H, sometimes there's more than one product. I just put a P there, and I did that in all these cases to indicate that there's some set of products, but we don't care for the moment what those products are, and we don't even know how many of those products there are. This is a first order elementary reaction with molecularity 1. Here's a second order elementary reaction with molecularity 2, right? 2A means A plus A, which means that some kind of collision between two like molecules, 2A molecules in this case, to form some kind of product. But you could also have a collision between two different kinds of molecules, between an A and a B, and so that's also second order overall. And that's also got molecularity 2. So it's also a second order overall elementary rate law, or elementary reaction. There's a rate law associated with each of these. Now, I didn't say it above, but let me say it now clearly, that you can't write the rate law for an overall reaction. The overall reaction doesn't tell you enough information in order to know what the rate law for that overall reaction will be. So for example, 2H2 plus O2 goes to 2H2O. We don't know what the overall rate law will be. Let me write here. Yeah, I'm sort of out of space here. But anyway, we won't be able to write the rate law for this. We won't even be able to tell necessarily whether the rate law depends on reactant concentrations, whether it depends on both reactant concentrations, or whether it also depends on product concentrations. The rate law can, in principle, depend on product concentrations. It can depend on both reactant concentrations, but it may also not depend on all these species. It usually, in fact, doesn't depend on the product concentration. It usually does depend on both reactant concentrations, but not necessarily. It may depend just, for example, on the H2 concentration, could depend just on the O2 concentration, and it doesn't necessarily depend to the first power any other known power. So for an overall reaction, you can't write the rate law down. You need a mechanism, like we talked about above. You need a whole set of elementary reactions like this. That mechanism will allow you eventually to deduce what the overall rate law is. But the overall reaction by itself is not enough information. However, for elementary reactions, you can write the rate law down. And that's because they're simple. There's only one reaction. An overall reaction really involves a whole set of elementary reactions at once, and that's why you can't tell what the rate law is going to be. But an elementary reaction really is just one reaction. It's not a stand-in or a symbol for a whole bunch of other things. It's a symbol only for itself. And that means you can write the rate law for an elementary reaction. So for a first-order molecularity 1 reaction like this, the rate law is always a rate constant times the reactant species to the first power. Molecularity 1, first power. Only the reactants show up. The products never show up in the rate law of an elementary reaction. The products may show up in the rate law for an overall reaction, but that's because it's got a whole bunch of other reactions buried inside of it. And in some of those reactions, the products that appear here are actually reactants in some of the elementary reactions inside of it. That's the way products end up in the rate law for an overall reaction. But that can't happen for an elementary reaction. So for an elementary reaction, products never show up. And for a first-order reaction, it's always just the reactant to the first power. For a second-order reaction, yes, it's the reactant in this case to the second power. It's molecularity 2, second power, those two go together. If you've got two different kinds of molecules or species in this case, it's the product of both of the reaction concentrations involved. It's overall second order, it's molecularity 2, but both reactants appear only to the first power because that's what you need in order to, because there's only one of them, right? The 2 here corresponds to the 2 there. There's only ones here, and so there's only ones here as well. In general, if I have an elementary reaction that looks like this, now you never have an elementary reaction that looks this complicated, but okay. I write it down to just illustrate the general case. Then the overall rate law will be, you can tell what the powers will be in the rate law by the stoichiometric coefficients in the reaction. The powers are the stoichiometric coefficients for an elementary reaction. Again, that's only true for elementary reactions. All right, that is the beginnings of the beginning, and I think we'll stop there and pick up what comes next in the next video.